So we're looking at the classical version of pen that actually works. Oh, here we go. Let's see up here. So when we had quantum mechanics here, what did we do? We had this energy level, still this. What this ended up becoming, this minus GQ 2m H bar m sub s b. That's what we had. So we ended up with these discrete levels, depending on the m sub s value. Okay. This is E here. This is dependent on the m sub s levels. We do a classical mechanics. So this would be if you have a B here. So this is going to be like this. This mu can only be at certain discrete levels like that. That's what this picture here. Or classically, this is B, if this is mu, the mu can be anything else. Okay. This is theta. And so in this case here, the energy is just minus mu dot B. That's a change, but this just goes to minus mu B. Okay. So we have to account for all this, and also we have to account for here for this as well. And so in this case here, we have our Z is going to have the same form, more or less, with the exception of the next one over H here. The sum on I, actually, this one will not be because of we still have this. So we have to sum over all things, and we said what we have to do is actually go over all the sum. So last time we ended up with this. We had Z and we had it just for one particle. We had this, we're going to sum on all the theta, all the phi, and this guy here. So that really goes to integral on theta, phi. And the theta goes from 0 to pi, and the phi goes from 0 to 2. Okay, so we're going to do this integral. So, okay, so I'll be a nice guy, and I'll do the phi integral. The integral of d phi is phi, okay? If you evaluate it at 2 pi, you get 2 pi. So the phi integral is 2 pi, okay? There, that's what we have. Okay, you did the rest. I mean, I did half of it for you. Wow. Okay. You can actually do this one kind of easy because what do you notice about sine of theta? The sine of theta is the derivative of?
It's derivative of minus cosine.
Yeah, up here. So what does that look like then? Always ask you can do it as a U sub, but I always try to get people out of the habit. Oh, yell at me here. Tell me why this is not correct. I mean, mistake. -1 for the teacher. This is correct.
Oh,
This is not correct.
the energy is minus, so it has to
This
be
is-
positive.
Well, that's what I can do since I'm using the superior technology called marker. There, that's fixed. Yay. Okay. Keep me on this. Okay, so always try to ask yourself the reverse question. What do you have to do to differentiate to get yourself this? So you know it's going to have to be something with the e to the UB cosine theta over CBT. And I just figure out what you'd have to basically, so if you differentiated this, what would you do? You get a minus sign. And then that would all, you get a minus sine of theta, but then you'd also put it on the mu of b and a QBT. So to fix that, what would you have to put in front?
Minus KBT over BB.
KBT over B. And this is the value we can do. Okay. So if you do this, what do you get? You get this minus 2 pi KBT over UB times e to the minus UB over KBT. And I subtract the lower limit, and this is minus e to the UB. KBT. That's really sad KBT. Hey, and I think we have a friend here. Let's make that look a little more friendly.
Yeah, multiply by 2/2.
So, okay, I'll do, the other here, 2/2, excellent. And then I'll distribute through the minus sign. So if I multiply by 2/2, you get Z1 equal 4 pi KBT over mu b. And then what do we have? We have then the e to the mu b over KBT. Minus e to the minus mu b over KBT over 2. Over 2. And that's a friend, the
That would be
hyperbolic.
sine.
Good job. Okay, that's our hyperbolic sign. So this is Z1 equals 4 pi KBT over mu b. Hyperbolic sign, often called the if you want to hyperbolic cosine, you see is cosh. This one we call sinh. Okay, so this is a sinh. UB. But just notice if you have this, if you let x be by definition of this argument here. This z here. This 4 pi sinh of x. This is 1 over x, yeah. Okay. Okay, now we want to find something here. We want to find. We did this, actually, we mentioned this a long time ago. We're going to go through the argument again. We want to find the average z magnetic moment for this thing. For that one particle. So let's figure out how we just write. So how do you do any expectation value with buttons? Okay, let me point. How do you do any expectation value in statistical values?
Sum on I.
Okay, so we know that this guy here, I need to let's put an X here. We have sum on I.
Of x sub I. P sub I.
Piece of I. And we know that this becomes what? This is this X of I. The piece of I becomes really
That would be
e to the
minus e sub I.
E sub I over ET.
Over partition.
So we know that. Okay. So what we want is the following. We want this guy here. So let's first of all figure out how to write this. And again, this is just for one part. You're going to have a sum on I. Now, how would I'll put the mu z e to the minus e sub I over kt. I'll put a little I here. This is going to be the single component of the state. Now, what would this fellow be?
I would be.
Let's draw a little picture. Here's a mu. Here's a b. And here's a
mu sine theta.
This is the axis.
Mu cos theta.
There you go. If you look at this guy right here, mu z is mu. So what we really want to do is this guy here. And I want to make sure I'm not coming off the edge here. That is the unfocused thing I've ever seen. Maybe, can I fix this? I guess it's okay. But I am getting to the edge there, so I'm gonna stop right there. I'm gonna go back to the chair. This will be a sum up of this mu. Cosine, let's say theta line like this. Okay. Let's e to the minus mu b cosine of theta. Okay, I'll put it like that. Okay, you're gonna have to sum over. I'm sorry, go sum over all the theta and all the phi. QBT. That's what we want, right? This right here is your mu. Okay. Now we've seen this little trick before. Okay. What does if you write this here? Okay, what does this mu be? How can I get a mu? How can I get a mu cosine of theta? What can I do with this term?
Take logarithm? Or no?
We're going to take a logarithm. But if I just had this guy here, what would happen if I differentiated this with respect to p? I had this. I think we're doing this with respect to theta. Yeah, pull out a mu cosine of theta over QBT. So that's kind of looking like this. So we're going to think we're going to want to do some sort of derivative with respect to the magnetic field. What we need is z down here too. So we had this before. So we're going to kind of guess on something. We're going to look at the logarithm of our partition function. So we're going to look at logarithm of z here. And what do you think we're going to do to it? This is a z that's in terms of the, right? This guy here is this summon I e to the mu b cosine of theta QBT. Now that sum is going to be a sum of theta and so on. That's what that z is. And what do you think we're going to do to that?
The derivative with respect to the B field?
Yeah. So we're going to look at this and take the derivative with respect to magnetic. Okay. So if we do this, so let's actually calculate this out. This is d by dt of the ln of sum on theta and phi e to the mu b cosine of theta. Okay, what do you get? I take the derivative of a logarithm.
It's 1 over the argument.
Okay, so you have a whole mess in the bottom. What goes in the top?
Derivative of the argument with respect to the derivative. So it would be,
So we have this, so we're gonna have the derivative of this whole thing now with respect to b, so this will be the sum on theta and phi. The exponential just comes along for the ride. What goes in front?
you get mu cosine theta over KBT.
mu cosine of theta. Okay. So take the K, so this is nothing but what?
That's our partition.
That's our partition function Z. So I'm gonna multiply everything through B here by the KBT. So you take the KBT to the other side. So you write this as KBT. Part d by dt. It's really a partial. I'm cheating here. I'm left with this. Hey, does this side here have a name?
That's the expectation value.
That's the expectation. Ta-da! That's very slick. That makes sense? Yep. Now that's for how many particles?
One.
That's for one. Let's generalize this now for more than one, because we're looking at a system. So let's generalize this. For more than one. Spin. So we're going to assume that the spins are not interacting. So assume that the spins are non-interacting. Now we know what happens here. If the spins are non-interacting, what is the Z for that entire system?
Z1 to the end.
Exactly. So we know, but I want to go through that argument again because this is important. So for non-interacting systems, okay, what you do is that Z is becoming Z1 is the end power. N is the number of non-interacting particles. And the Z1 is the partition function. For one particle. We've seen this before, but it's an important enough argument. We're going to do it again. For this case here. Okay. Proof. Okay, you tell me. We're assuming that all the particles have the same mu. So here's our system. We have, here's the B like this, here's B's, this is the B. Maybe you just want, this is mu here, this is at some angle theta 1. Here's some, yeah, I'll go with this. Which is theta 2, here's the mu for that guy. This one's like this, theta 3. This is here, and then this one over here. This would be mu here like that. We have all these particles here. They're all different things.
For the theta 2 there.
Yep.
Wouldn't that be going the other way?
Tell me why that'd be fine.
Feet. Okay.
Okay, so how do we write this? We know that we have this guy here. But this EI is what this EI is energy for the entire system. So what do we have to do here? Let's get the E first. We get E to the minus. And what would you have for the entire system? You have minus mu b, the first particle, mu b
UV cos theta 1.
cosine theta 1. Then for the second one, you have minus mu b cosine theta 2, and then so on and so forth, all the way to the last one. Does that make sense?
Yes.
And then you divide the total energy by kVt. Now we have to sum all of these here. So what?
So we're assuming that all mu's have the same value?
Yeah, we're going to assume that all the particles have the same magnitude, and the b is the same for all of them. The only thing that's going to differ is going to be the theta. Okay, so what do we have to do? We have to sum over. For the first particle, we have to sum over all theta 1 and phi 1. For the second particle, we have to sum over all theta 2 and phi 2, and so on and so forth into the very last one, theta and phi. Okay, now you're pro, you've seen this before. Now what?
We can break it up to so that each sum is acting only on that.
You can break up the, you can break this exponential up, the whole bunch of exponentials all being right. This one from here. You can write it as e to the mu b cosine theta 1 times e to the minus mu 1 mu b cosine theta 2. That's all these terms here. So I can take one of them, put it with this guy, the other one, put it with this guy, and likewise all these. And that one, and then this guy. And make sure that's fitting. Is just fit. All those. So how does this term and this term and all these terms compare?
They're the same.
They're the same. So this is going to be z. It's going to be just this theta 1 phi 1 e to the mu b cosine of theta 1 all raised to the n power. So this is nothing but z1. So this is why we have the famous z z1. Does that make sense?
Yep.
Okay, any questions? So what we can do is I can really just say that in our case, we're gonna have this 4 pi this kb over t ub actually. Okay, so the c is going to be this guy. It's going to be this 4 pi kb t b cinch ub bt all raised to that power. And it's the exact same argument to get the other, you get the total magnetization. It'd be there's no variation. Is that okay?
Yeah.
Okay. So what we have here, if I want this mu then z for the entire system, this is going to be this kb t. You should really be writing partial. d by dt, d by dv on this logarithm of this. Okay. So let's actually do this. So what do we got? I'll be nice and copy down the KB.
PBT. Partial respect to be of.
So it's going to be the logarithm of this guy.
And
And then I can just treat this as kind of like 3 factors.
yeah,
I have the ln of 4 pi, which I can throw us out. Plus n times the ln kb t. Actually. All right, let's keep it. Minus n ln ub. It'll just be easier to work with it this way.
plus ln of the, or n ln of the hypothesis.
Yep. And there's nothing you can do with that piece. Okay. I'll be nice and do the constant. The derivative of the constant with respect to the negative 2 is 0. I'm going to do this piece here. This is a function of no b dependence. This is 0. Okay. We're left with kb. 0 and 0. This guy gives us
Minus
n.
mu over ub.
Okay. So take this from the bottom, ub. And the derivative of this with respect to b is u like you said. Then plus n. Okay, what's that one?
It would be 1 over the sinh u.
So the sinh goes in the bottom.
PBT times
Is that actually? Yeah, you can still see it.
push mu b over
Hyperbolic, the derivative of the sinh goes to a hyperbolic cosine. So over the cosh, the mu b
times
kbt.
mu over kbt.
That's the derivative of the interior with respect to b, which is this mu. That makes sense?
Yep.
Oh. Okay. Yeah, okay. So cosh over sinh is
Hyperbolic cotangent.
exactly. That's your hyperbolic cotangent. Okay, so we're left with this is okay. Both values have n here, and I can factor out the mu here. I'm going to write this guy first. I'm going to write this guy first. This kdt cancels that kbt. I'm going to pull out the mu in the end. So I can pull out both terms have a mu. Okay, then what does this term become here? This becomes the hyperbolic cotangent of mu b. Okay. Right? Is this term here? Cancels this term here. And I have a mu and an n that I pull factored out.
Okay.
So this is what this is at. This term, I have a mu and the n that I factored out. So I get a minus sign here. Minus. And left with kb t. So this right here, I can let mu be kbt. If I plot this, this is x. You get a graph that looks like this. So where would be large T on this graph?
You would get that would be at low X.
This right here, this is gonna be, this region here is gonna be low, large T, or low.
Or low B.
This region over here is gonna be,
It's gonna be low T or high B.
this will be low T or high B. It turns out that this thing's actually gonna flatten out. But this value right here, this is really neutral. Let's see if we can make this sense of this. Why would the magnetization, if you look at the mu sub z here, why would that go to 0 for like high T?
For high T, you have a lot of thermal energy in the system, which would cause the spins to be in any direction, regardless of the B.
Remember those polar, the probabilities actually go to a constant. So this and this and this and this and this, and all those are equal in length. So you can have it anywhere along here like this. So you can have the spins anywhere along here. On average, this is going to be 0. Does that make sense? And what about low B?
You would have, looking at the X term, it would be low X. Physically, there would be almost no torque on the magnetic moments causing them to one, so they would still be random.
Exactly. Yeah. Now, go the other way. High B.
The high,
What are all the spins going to do?
they're all going to line with the B field.
They're all going to line up the spin of the B field. So what would you then have? Well, your mu then would just be the mu for 1 times the number of spins. Makes sense. Same with low T. If it's low T, where are you going to find the system? It's going to be in the ground state. And in the ground state, all the spins are over. Okay. So actually, that makes perfect sense. Okay. Now, let's do a little review about what was magnetization. Okay, there's something called magnetization. Now, how do we define that? We said if we have some material here, so here's some substance, here's some system. What I can do is I can look at a tiny little volume. This is a small volume. Let's say that's some volume V. And we define the magnetization M. How do we say we define that? I think
Is it integral of UdV?
no. We're gonna look at all the magnetic moments inside here. So we're gonna look at a sum. These views of I side. So this is basically this is the total. This is the sum. All the mu's and i's. All the little magnetic moments that thing. Divided by the line. So if we want then M sub z, it's just going to be the sum on I, this mu iz. So we have this. So all I'm going to do is I'm going to take this guy here, this right here. This is really going to become what? This is really going to become our area. Well, actually, let me do it. Okay, if I multiply the top and bottom here by number of particles in here, what am I left with? this guy here is what?
That would be your average.
That would be your average value. This right here. That'd be your number density. So what you're gonna have here is that you're gonna have this N over B. And this mu z here. Okay. So what we're left with is this is the number that I'm saying this we call little. Okay. Yeah. Now in our case here, this right here, this is the average for one particle. In this case here, this mu z is actually the average for all the particles. So this here, this n times here is really the sum.
Okay.
So what we have here is if I want this for this system, I'm going to take my value here and just divide it by the volume V. We're going to have this n mu, I'm going to divide this by V. Cotangent x. That makes sense?
Yeah.
Okay, now, if it can be shown, who do you think is going to show it? You two. Okay, it can be shown that hyperbolic cotangent of x minus 1 over x reduces to x over 3 when x is large. I'm sorry, when x is small. Because we want to do the large t thing. This corresponds to so we have here that for large t, with this. What did we say x is? Mu v over now, this is called, okay? You might recognize this. The fact that the magnetization is going with 1 over temperature. That is called Curie's law. And that's actually a fundamental derivation. Curie's law. Oh, fundamental in the weak, the non-numeric. Okay. We do one other thing with this. I'll just submit that. Does that make sense?
Yeah.
Okay. Now we want to do what have we assumed about the gases so far? We've only looked at gases where the interactions have been zero. How do you start dealing with interactions of 0? So we're not gonna go all the way to full-fledged interactive systems, but we are gonna consider weakly interactive systems. So what I want to do now is talk about how do you account for weakly interactive systems. And we're gonna modify the ideal gas law, you might know this. So you modify the ideal gas law, what does it become? The van der Waals equation of state. So I want to show you where the van der Waals equation of state.
Yeah, this was something that we, I think maybe touched on, but we didn't spend much time on it.
Oh, we're gonna spend time.
Yeah.
Oh, we're gonna hit it, okay. So what I want to do is start looking at weakly interactive systems. Okay. So, and so when we did the ideal gas law, what did we do? We set potential energy equal to 0. Now it's not going to be 0, so say that. So in a case like, okay, why don't we just end it here? Then we'll pick this up on Friday. Okay.
Okay.